evening, everybody. I'm Amy Miller. I'm on the faculty here at Northeastern, and I have the honor and pleasure to be the MC and host of tonight's event. So my job is to kind of keep us on time and keep us moving forward so that we can all enjoy the talk that we are here to hear about from Gray. As many of you probably know, this is an annual event. So the Freeman Lecture is the central event that the Freeman Committee is responsible for. I'm a member of the Freeman Committee. There are a number of other members here. If you could all raise your hands. I think they're mostly up at the tables here, kind of in the front. It's a consortium of about a dozen individuals from different universities around, mostly actually all of Massachusetts, as well as folks from consulting and the public service and government sector also. So we try to represent a lot of different perspectives on this committee and think about that in designing this annual lecture. So I will tell you a little bit more about the Freeman Committee and the Freeman Lecture in a minute. Before we get started, I would actually like to hand off to our colleagues from BSCES, and they're going to give you a little bit of information generally about the BSCES chapter here. So first, I'm going to hand it off to Emmanuel.
Thank you, Amy. Good evening, everyone, and welcome to the 2026 John R. Freeman Lecture. My name is Emmanuel DeAndre, as Amy mentioned, and I am the current Environmental and Water Resources Institute Boston Chapter Chair. The Boston Society of Civil Engineers section of ASCE, otherwise known as BSCES, fosters the professional development of its 3,400 members in their organizations by offering diverse technical lectures in various disciplines of civil engineering, legislative advocacy, public outreach, and awards and scholarships to deserving recipients. Our efforts help our members advance their careers and maintain a competitive edge in the global economy. All of this is made possible through the efforts of member volunteers who are active partners on our 9 technical groups, the Government Affairs Committee, Outreach Committee, or as liaisons to 10 student chapters. I encourage you to visit our website and find out how you might become an active member of the Society. I would be remiss if I were to not thank our generous Society and program sponsors. Without their support, BSCES would not be able to undertake the wide variety of technical events we conduct each year. The Society sponsors for 2026 are AECOM, CDM Smith, Keller, Menard USA, Skanska USA Civil. Our program sponsors include Beals & Thomas, Banesh, Beta, CHA Consulting, Collins Engineers, Dewberry, Geocom, Gill Engineering, GZA, Green, Hilly and Aldridge, HNTB, Howard Stein Hudson, Oil and Tanner, Kleinfelder, oops, I guess I went too far, sorry, Northeastern University, Department of Civil and Environmental Engineering, MP Engineers Plus, PMA Consultants, SGH, Stantec, STV, Cervicos, and finally, Vaness and Associates. With this, I would like to turn it over to BSCES President-elect and Acting President, Rich Madsen.
I don't have a formal speech, but I just want to introduce myself as acting president for BSCES right now. And just wanted to thank Northeastern, EWRI, and the Freeman Committee for putting on this event. This is just one of many events that BSCES puts on. I think this year we're looking to get about 35 plus events. We do a lot of technical tours, webinars, different lecture series. We'll do some social events as well. We also give out student scholarships. So for the students in the room, we're giving about 40,000 this year, pretty significant. So deadlines have already passed, but if you're still a student next year, be on the lookout for those. If you're part of your ASCE student chapter, I know there's a lot of PhD students, so maybe not. But we also give out student grants for the chapters, and those are actually due by this Friday. So if anyone's looking for money for your student chapters to put on an event before the end of the year, reach out to BSCES. We got some money for you. But with that, yep, thank you and enjoy.
Okay, so the main event. Before we get to the lecture, I wanted to give everybody a little bit of history about what is the Freeman Lecture, just so that we can put this in context. So I've tried to summarize the key points for you here, but John Freeman was a really remarkable civil engineer. He was a graduate of MIT, but then went on to do really iconic projects across the country that probably many of you have heard of or seen or taken advantage of yourselves. So in 1925, he actually endowed a gift to BSCES to promote kind of awareness and I honestly, like, I think of it as professional joy among young water resource engineers. And the idea here was really young does not just mean students, young also means engineers who are starting their career, who are developing in what they're professionally working on. And so we think of this lecture as an opportunity every year to bring together all of those people from students through every stage of professional life to think about something related to water resource engineering. And you've also probably experienced that has started to change in meaning over time. So it's not just hydraulic engineering anymore. And we try to think about what is new and interesting in this field for our lecture every year. So we hope this annual lecture, which is in the memory of John Freeman, brings that excitement to all of you today, and that we'll see you in future Freeman lectures, which we do pretty much every spring. I did also want to highlight, in addition to Rich's comments, that the Freeman Committee also has some funds available for student professional development and student projects. So that's also something for you to check out on our website and think about in the future. Okay, so before I hand over, I wanted to just go over a few points of housekeeping so we're all on the same page. This lecture is being recorded. The camera is only facing up here at the lectern, but I want you all to be aware of that. And then also in the Q&A, we'll try to repeat questions so everybody online can hear as well. The dessert and the food will stay out there during the whole lecture. If you are snacky, please just try to not create too much of a disruption, like winding your way back there. And the restrooms are in this little side hallway, so you don't actually even need to leave this room. You can just go out the side. And if everybody can turn off their cell phones, which is always just a thing I feel like we need to do now, that would be greatly appreciated. And with that, I want to hand over the lectern here to Dara Entakabi from MIT, who is going to introduce tonight's speaker.
Good evening. It's a great pleasure to introduce Gray Nearing, who works at Google Research. He works on things, for example, right now, such as the Google's Flood Hub, which is an operational global flood monitoring and warning and alerts. If you go to its webpage, and I'm sure it may show some of that. At Google, he works in Google Switzerland. And I just learned today that part of that reason is to work very closely, which she has at Google, with global organizations like the various UN branches, as well as developing private partner relationships, which is one of the emphases that he has had. He got his degree from hydrology in the University of Arizona, and that's the first time our paths crossed, maybe not synchronously, but asynchronously. And ever since then, we have crossed paths asynchronously. Before going to Google, he held faculty positions at UC Davis and University of Alabama, the National Water Center home. So with that, I would like to welcome our guest to Boston and welcome you to the lecture.
Okay, hello. Arrow keys, perfect. Okay, So I have this bad habit of not keeping the microphone up to my mouth, so feel free to jump in and tell me this. It's a recurring theme. Okay, first of all, thank you so much for inviting me here. It's really an honor to be here. It was really a pleasure to hear from Dara when he reached out. I worked for Dara, I guess it's maybe fair to say, back in my youth when Dara was launching the SMAP mission. It was just an amazing experience. I remember being a master's student and going with my advisor and sitting in on some of the SMAP science definition team meetings and thinking, oh, this is what I want to do in life, and this is so cool. And then just seeing Dara be able to put all this together. So it's really, really a pleasure to be here, and thank you very much for the opportunity. Okay, so I want to talk about something that I care very much about, which is hydrological modeling. And I'm not sure why I care so much about this, but I really do, and I hope that it comes across in this talk. And I'll just get started. Okay, where we go. Cool. So I'm from Google. Google does not have a hydrology team. I was, as far as I know, the first hydrologist that Google hired. Probably not true, but I did learn that we have another one. There's another PhD hydrologist that was hired in Google Cloud. And that's been fun to have lunch with this guy. But so we don't do hydrology. So why are we doing hydrology? And the answer is this. This is why we're doing flood forecasting. The reason is because people come to Google for information, and they come to Google for information relevant to us during times of disaster. And we see that as hits on all of our main core products. So the first thing that I think is worth saying, although it doesn't really matter to anyone in this room, it matters to a lot of audiences that I talk to, is we don't have a revenue stream. We don't do any of this for money. We do this for money in the sense that we're serving the core Google customers across search, maps, weather, and a few of the other services that people use every day. We'll get back to that, but it's important to understand that this is the reason for what we're doing, and this reason shapes a lot of the things that we're going to talk about. As one of many segues tonight, one of the things that this means is that, first of all, I'm not a civil engineer. I was a little bit intimidated to accept this invitation because I don't really have anything to say to civil engineers. I don't really know anything about civil engineering. And I certainly 100% would not recommend using my model or any model that I've ever built or anything related to my model for any civil engineering infrastructure decision. And this is really important because this is a machine learning model. It's now, I'm really proud to announce for the first time this month, it's now an AI model. We're doing flood forecasting with AI, not just machine learning. We'll get to in a minute. But it is a model that's designed for a purpose, and the purpose is flood forecasting. And you would not want to take the outputs of this model, which you'll see in a minute, and do things like design infrastructure with it, or estimate stream flow with it, for example. Okay, you wouldn't want to operate a reservoir with it. There are companies that take the models that we built and use them for reservoir forecasting, but we don't do that. And it's really important, especially in the case of machine learning and AI, that you use models for their intended purpose, because these things are not comprehensive descriptions, physical descriptions of systems. These are things that are built for a purpose. Okay, and that's one of the things that I like best working at Google, is because we have a purpose, we have customers. Our customers are Google Search, Google Maps, Google Weather, and we fill the needs of those customers, and I don't have to guess what people might want from me. It's very clear. Okay. So Google does a lot of this stuff. Before ChatGPT was released in whatever year that was, Google Research was looking for projects to work on, and we got deeply embedded in a few areas. Education, health, and climate were the three big ones at the time. And so we now, some of that work is coming to fruition, and we now have models that predict most types of natural disasters. We don't get involved in conflict disaster prediction at all, which is usually the first question that I get in a normal audience that I talk to. But we have floods, wildfires, cyclones. Floods was the first model in the climate space at Google, and we kind of laid the groundwork for all the others. And now we have, of course, probably everyone's read the New York Times articles about our Google's weather model called GraphCast and the hurricane predictions that we're doing with NOAA based on that. And we do wildfires. So we launched a satellite and soon to be a constellation of satellites with muon space to observe wildfires. And we build AI models on that data that we collect from that. And we try to provide this wildfire boundary detection and early wildfire detection to first responders. So we kind of look at, we had an earthquake forecasting project that was actually on the team I work for, and that didn't work out so well. So we don't forecast earthquakes anymore. Okay. Interesting segue. Again, one of many. The Earth. So imagine you're in. I'll tell this story again later. But imagine that you're a hydrologist and you go into Google and you sit down and they say, "Okay, can you help with flood forecasting?" And the entire company are computer scientists, and so you get situations where a group of Stanford computer science graduates, bless their hearts, all great friends of mine, sit down and say, "Oh, I think we can predict earthquakes." And I guess there are probably enough people in the room with a geology background to know how silly that thought is. But anyway, this is the kind of thing that happens, and I love that because you get a bunch of people that are really, really good at what they do, and don't always know the boundaries of what is and is not possible. And sometimes you find out that those boundaries are not as correct and firm as you thought they were. And it's a really exciting place to do this work. Okay. So this is the slide that everybody at the UN wants to see, because why is Google telling people about disasters? We're a private company. This is not our job. It is the job mostly of national and local governments. And so I like to explain how this fits into the project of disaster warning at Google. First of all, we have to do disaster warning. We don't have the option not to, because we give more people more types of information than any other organization in the world. And people ask us for information about natural disasters. And if we don't decide what to show them, meaning if we don't show them government alerts, they see other things, which are oftentimes correct, but oftentimes a mix of misinformation, disinformation, and sometimes outright warfare. We've seen several cases of that, where adversarial governments have search engine optimized bad information to harm people. And so we try to make sure that people get correct information, and we do this through a range of sort of 3 different programs. This one is public alerts. This is the most important one, and this is where we go out and ask governments to give us official alerts. And we don't work country by country. We do work with many countries. We have a partnership with 32 countries in Africa, because Africa is often underrepresented in sort of the global alert aggregating platforms. But mostly we use global alert aggregating platforms to fill this gap. CAP stands for the Common Alerting Protocol. This is the standard that the UN has adopted for international alerting, and they want basically everyone to use this standard to disseminate their alerts. And there are a few organizations in the world, a couple of them public, a couple of them private, that try to aggregate these alerts, and we can pull from these global feeds. The most important one is called the Filtered Alert Hub, which is used by the WMO, World Meteorological Organization, and the IFRC, the Red Cross. And so we pull from this and we try to fill the space of these requests across the standard Google products from these public alerts, which are the official alerts, oftentimes the official alerts from governments. This is the best option. Over here, we have this program called SOS Notifications. What that is we have teams of people, and I don't know how many people, but it's lots and lots of people that just spend every day curating news feeds and social media feeds, looking for signs of a disaster. And if they see enough signs, and they're really good at what they do, if they see enough signs, they turn that manually into an alert. We say, okay, there's enough chatter coming from this social media stream and this news agency and this on-the-ground humanitarian agency that we think something's going on in X country. And we put all that information, or they put all that information together, and they issue these things called SOS alerts. So these are Google-generated alerts from human-centric data. And that helps some. It's incredibly expensive. And then the last thing we call GIAs, Google-initiated alerts. And that's where we have alerts from our own models, our own forecast models. And GIAs fill the gap, right? The idea is that GIAs, Google-initiated alerts, fill the gap in what's missing from public alerts. Okay, so that's kind of how we fit into this ecosystem and what we're trying to do with our flood forecasting model. what does the ecosystem itself look like? So this is sort of a cartoon version of the ecosystem. Anyone that actually works in disaster management, disaster response will see immediately how incomplete this picture is. I've never once spoken to someone who actually works in disaster management that likes the model that the UN's built, but this is the UN's model. This is called Early Warnings for All. Early Warnings for All is a UN-wide initiative to cover every person on Earth with multi-hazard early warning systems by the end of 2027. It's been around for some number of years that I probably should have looked up before I stood up here on stage to tell you about it, but it's several years and it's a few $1 billion have been invested in this. And the goal is, how do we make sure that the global population is prepared for all of the types of disasters that we are able to forecast? What does EW for All look like? It's called Early Warnings for All. Everybody calls it EW for All. Well, it has 4 pillars. EW for All has, the first pillar is risk. This is, what does population exposure look like independent of any disaster actually occurring? We call that risk, and that's led by the UN Office of Disaster Risk Reduction. And they do things, just look at population exposure to things like earthquakes, floods, fires, these kind of things. Then we have the hazard, which is the actual, okay, we're making a forecast and something's about to happen. That's the pillar 2 is led by the World Meteorological Organization. And they're basically a collection of national hydromet services. So every country, almost every country has a national national meteorological hydrological service. It's very important that you get meteorology before hydrology. I learned the hard way as a hydrologist. NMHSs, they're called. And the WMO is a collection of NMHSs, and their job is to organize how governments share data and share ideas and share information when and where possible. By the way, it's much harder to share data and harder to share information in hydrology than it is in atmospheric sciences, because everybody knows and has known forever that atmospheric circulation patterns are a global phenomenon, and it's just natural to share a lot of weather data. Hydrology is very different. Water data has economic implications and national security implications, and it's much more difficult to get countries to share water data. It's also much more difficult to get them to collect water data because there isn't quite as much value to it, but that's a separate problem. So we have sort of unique problems at the hazard level. And then we have pillar 3, which is dissemination, and that's led by the International Telecommunications Union, which is the UN agency in charge of telecommunications, cyber communications, these kind of things. And they're responsible for understanding how to get people the messages about the hazards once they're generated by the national Met services. And then we have response. Pillar 4 is response, and that's led by the International Federation of Red Cross and Red Crescents. And they're the ones that actually have boots on the ground to help people, and their main things are these disaster relief emergency funds, DREFs, they call them. There's international DREFs and local DREFs, and they try to release money to help people recover from disaster. They try to have people on the ground to help people prepare for disasters. And more recently, much more recently, they do these things called early action protocols, which are trying to get money to people ahead of disasters, because $1 is worth about 9 times as much if you get it to someone before a flood as it is if you get it to them after a flood. You can be wrong about a lot of floods and still come out ahead in that math. So the IFRC is developing this set of protocol called EAPs, early action protocols. They're location by location, really down to like the river level, what a specific IFRC EAP will look like. And this is saying, okay, if some forecast model predicts that a flood is coming with X confidence, X days in advance, then we're going to release we're going to pre-position aid, or we're going to release pre-disaster money. And again, you get to be wrong a lot of times and still come out ahead with IFRC. They're a very easy organization to work with. Okay, so back to Google. Google's entering this space. If you left it up to the software engineers at Google, what you would get, and I'm going to describe this in some detail, you would get something that looks like disruption in this space. Maybe that's worth just saying here. Maybe it's worth going back here and just notice that the role that Google plays in this space is pillar 2 and pillar 3. Okay, we could probably do risk maps. We don't. It's not part of what our customers are, people coming to Google search are looking for. And if they do, you can show them something from a peer-reviewed paper or something. But we do hazard forecasts and we disseminate to the world. We're the largest dissemination organization in the world, right? And we're also now, at least we tell ourselves we're the largest forecasting organization in the world. Almost certainly that's true. I spoke to the director of ECMWF a couple weeks ago and he agreed with me when I said that. So I'm pretty confident in saying that publicly. Okay, so we can connect these two pillars of the EW for All ecosystem for free. It's not really for free, but it's measured, I don't know what the budget is, but it's going to be measured in some millions of dollars as opposed to billions if you do this with different agencies. If you take the national forecasts, you try to get those forecasts to some dissemination tools. These are telecom services, internet service providers. You're connecting hundreds of organizations, dozens at least, hundreds of organizations around the world, trying to get them to coordinate to get people information. And we can do all of that under one roof. Okay, so what this really means from the perspective of EW for All is that we've increased the efficiency of at least two portions of EW for All by several orders of magnitude. I don't have the dollar figures, but it's going to be several orders of magnitude, right? So, you know, this is a threat, this is a problem. And if I were speaking to you in Geneva, there would be a lot of you who would be really, really angry right now. And they get really, really angry about this because we don't want to privatize disaster warning. Nobody wants that. I don't want that. You don't want that. Certainly the people in charge of this portion of the world don't want that. But these efficiencies that we're able to achieve by basically doing forecasting in-house are too large to ignore, right? And this is it. So how many people do we talk to every day? This is a proprietary secret that I certainly don't know. Probably Sundar, the CEO of Google, knows the answer to this question. I have no idea. So I wanted this number to kind of illustrate how big this challenge is. So I asked our competitor, our main competitor, how many people use Google services a day, and I got the number 5 billion. So we're going to say that we talk to about 5 billion people a day, just to kind of put the problem in perspective, right? This is the number of people that we talk to for free that it costs other disaster warning, it costs the traditional disaster warning ecosystem a lot of money to be able to talk to, right? And again, what we really want, the ideal state for us, is that national governments make alerts from these multi-hazard early warning systems, put them on the global aggregators, and we absorb those. 40% of countries, this is according to a late report issued by the World Meteorological Organization late last year, 40% of countries don't have multi-hazard early warning systems. And for floods specifically, 33% of countries don't collect hydrological data and couldn't even build one if they wanted to. That's the bad news. The good news is that over the last 10 years, the WMO has managed to increase the number of countries with multi-hazard early warning systems by doubling, more than doubling it over the last 10 years. So we're seeing a lot of progress, but we're still covering only about 60% of the world and no real path to a lot of the rest of the world that's not being covered. One slide that I may or may not have in here, I can't remember if I took it out, is showing that the places in the world that lack hydrological data have the most exposure to flood risks, which kind of is probably intuitive to most people. Okay, flood warnings matter. This is the last thing that I want to say before we talk about machine learning. Flood warnings matter. So this is a complicated graph, and I'm not going to go through it. This was a study that was conducted by a professor at Tufts and also at the Yale Department of Economics. And what they did is they took our flood forecasts and they surveyed about 1 million people in the Bihar state of India, and they did A/B testing on whether villages got the flood warnings or not. And the bottom line is that with some appropriate prompting, and I can tell you what that prompting looks like, there's about a 30% reduction in post-disaster family level health costs after a disaster based depending on whether a village received an alert or not. So if a village receives an alert, then the family health costs after a disaster go down by about 30%. And that's not zero, but it's also a big economic effect, right? Okay, so these warnings matter. People really use them. It takes some legwork. We have to work with the IFRC to get people to use the warnings and to trust them. And frankly speaking, trust is probably our biggest blocker. We're not a national agency. We're not who people expect to get flood warnings from. And that's probably the biggest blocker that's standing between us right now and this type of this type of outcome that we want to achieve. So this is why we work with the UN, because this trust is important. We want to understand how we can leverage this efficiency at scale in a way that works with the ecosystem so that we don't disrupt the ecosystem that people have spent their careers building, but also because if we don't have the trust of the ecosystem, then the information that we're producing is not as valuable as it would be otherwise. So we need to figure out how to work with this ecosystem. Okay, so that's what we do. We develop partnerships. My entire life these days is trying to get sentences into blog articles like this. And so, for example, this was a blog article that was published last year by the World Meteorological Organization saying, okay, we're going to start using AI for weather forecasting at the WMO. That was a huge deal. It was 2 years of my life essentially went into getting one sentence about the collaboration with Google in this blog article, right? But we did it, and we're what we're seeing right now, the change that we're seeing in the ecosystem is driven by necessity across a couple of different fronts. One is that just that AI weather forecasting, flood forecasting included, is really powerful. So when GraphCast came out, I think it was in 2024, the skill difference over the ECMWF forecasts was about the same as ECMWF usually sees with 10 years of research, right? And we got that out of just building a machine learning model. And people will argue that, okay, well, the first machine learning model probably, weather forecast model, probably got the lion's share of the improvements, but we haven't even started to assimilate satellite data yet. We haven't even started to do, weather forecasting improves along, just generally speaking, at a sort of a, I'm saying this to people that know more about this than me, but generally speaking, at a pop science level, weather forecasting generally improves because of two reasons. One is because of bigger computers, meaning we can solve the fluid dynamics at a finer resolution. And the other is better satellite data, meaning we can get better initial conditions, we can do better data assimilation. And the machine learning models haven't even started to absorb that second dimension yet. So there's a lot of room for improvement left. So this is being taken seriously. More importantly, though, the machine learning models, and this is the main point of my talk, so we're just going to put an anchor here for the very end of the talk. But what these AI models are doing, both in weather and floods, is they're much, much cheaper and easier to run than normal models. So countries can stand up models now without having to have a whole team of software developers or even a huge amount of expertise, domain expertise. You need some to understand what the models are doing, but the cost of standing up these systems with AI models is significantly lower than it was with the traditional models. They take almost the flood models take almost no HPC. In fact, you can run my model on a laptop, and that's a really big difference because in theory, it would cost us nothing to supply the compute that would be needed if we could get every national government to run their own flood forecasting models. And that's a big deal. Right now, if you're a country, let's say you're Rwanda, because they're going through this right now as we speak, and you want to set up a flood forecasting model for your country, the traditional way to do it is to hire this company called Deltaris in the Netherlands and set up the Fuse system, the Delft Fuse system, which is the sort of gold standard for national flood forecasting. And it's free, it's an open source software, but it's so difficult to use that it costs $1 million to hire a consulting company to set it up and costs about $100,000 a year to keep it going. We can do that for a tiny fraction of the cost, and our models are better. Okay, so what does our product look like? This is what we're producing. This is the Flood Hub. You can go there now, and there are several models under the Flood Hub. So this is g.co/Flood Hub. It's a global model. If you're a flood manager in Boston or New York City and you go to this model and you say, is this model as good as the model I'm running? The answer is no. The answer is absolutely, it is not. This model is a global model that's designed to fill gaps in countries where we don't have hydrological forecasters on the ground, sitting at RFC, sitting at National Weather Service river forecasting centers, doing professional level jobs. That being said, the model's actually really good. So we have partnerships with about 24 or a dozen and a half countries right now, and we've done some benchmarking with very sophisticated flood forecasting models in countries that I prefer not to name so as we don't shame anybody, but countries with really long-standing flood forecasting agencies. And our models are competitive with those in many cases. So there's real information coming out of these models. Okay, so what are we seeing? We're seeing hexagons. Those are our river forecast models. That's where we predict river flow, and we predict whether river flow is above a 2, 5, or 10, or I think 20-year return period threshold. Those are the different colors on the map. And then we predict these little blobs, which these red blobs, that's what we call a severe significant event alerting model, the C model. That's where we take a little machine learning model on top of all of our river forecasts, and we overlay some exposure, some population data, and we get estimates of where we think that population is exposed to likely floods. And this is where we send out these red blobs here are where we send out notifications to people's cell phones. So governments sometimes ask us to, sometimes don't tell us not to, and sometimes do tell us not to send out notifications to people's cell phones. We communicate with every government on earth except for the ones we're not allowed to work in: China, North Korea, Russia, Iran, and a couple others. And so we communicate with every government on earth, and we ask them, we're going to show these flood forecasts on FloodHub. You have to come to the website to see it. And some countries say no. You can't see this anymore, but it used to be very clear that Ethiopia wrote to us and said, no, you're not allowed to show flood forecasts in our country, so we turn it off. And then some countries, we say, okay, and we'd also like to send flood notifications to people's cell phones. And if you don't want us to do that, tell us not to. And many countries say, no, don't do that. And some countries say, yes, we really want you to do that because we can't do it ourselves. And so if the country says yes, then if your cell phone pings from an area inside of one of the red dots, then we send you a notification to your cell phone. That means you don't go to Google search to ask if there's a flood. We tell you that there's a flood coming. And I guess most people here have gotten a push notification from the National Weather Service for some reason or another, and it kind of looks like that. And as an example, we did this, we used to do the national flood forecasting for India. We don't anymore. They've built their own models to kind of take over from what we were doing, but we used to do that there, and we would send push notifications. And then there's another model here, which is an inundation model. That's this blue thing here, and this is where we're actually predicting inundation. We don't predict inundation everywhere, but this is a model trained on satellite data to predict how the river flow turns into inundation on the ground. And you see that sometimes and sometimes not. And then there's another model on here that you're not seeing. Well, we'll get there. Okay. I want to talk about science for just a minute, and science in a very loose sense. I'm a scientist. I went to Google from a faculty position. My intent was not to develop products for Google search. My intent was to publish papers. And when I got to Google, this was the first problem that I wanted to solve. The problem that you're seeing, we talked about this a minute ago, the problem that you're seeing here is that the places in the world that have the least amount of hydrological data, this is the total years of streamflow data that a country has available to it across the entire country, not normalized for area, which is a very difficult problem, compared to the GDP of the country. And there's another plot that you're not seeing here that I'm taking as common knowledge, which is that GDP is correlated, or is anti-correlated with population exposure to flood hazards, which is true and published in a lot of papers. What you're seeing here is that there's an inverse correlation between an inverse correlation between the difficulty of building flood forecast models, traditional hydrology models, and the population exposure to floods. And for anyone in the room that's not a hydrologist, the way that you build a hydrology model, in this case is a model predicting stream flow, is you take stream flow data from a particular point in a river, and you train the model, you calibrate the model for that location, right? One of the few named problems in the field of hydrology is prediction in ungauged basins. Ungauged basins means a watershed without a streamflow gauge, and it is a classically hard problem to make streamflow predictions in places without a streamflow gauge in the watershed where you're trying to make a prediction. And models that do this, prediction in ungauged basins, like the ECMWF Global Flood Awareness System, which they call GLOFAS, do a very, very bad job of it and often don't beat climatology, right? So we're trying to figure out how can we make predictions in places that don't have streamflow data for building traditional streamflow models. And the answer is this. We take all the data that we can get in the world and we train a machine learning model on it. Okay, so this is our attempt to gather as much open public streamflow data as we can. This attempt is called the Caravan data set. I'm not going to belabor the point here, but it's a data set that we maintain, and it's a community contribution data set. It's the largest data set of streamflow data, the largest public open data set that you don't have to pay for of streamflow data in the world. And you don't have to invite us to be co-authors on your paper if you want to use it. I'm saying there's a few people in the room that would know why I'm saying that. Okay, so what we do is we train a model on all of this data, and what machine learning lets us do is it sees enough diversity in hydrological rainfall runoff response that it's able to make predictions in places that it hasn't seen. It can't make predictions in places that have no similarity with any other places it's seen, but it's seen so many places in the world that the chances of a particular watershed being out of sample from what it's seen are very small. Okay, so most places, we have data covering most of the hydrological and climatological envelopes of the world. There's some exceptions. We don't have much data in Siberia. We do have a little bit in Alaska, but we have enough to build models that have some reliability out of sample. And one of the interesting things that we found, this is my favorite plot of my career, one of the interesting things that we found is that the machine learning models do better when they're trained on data from more places, whereas traditional hydrology models are best when they're trained exactly where you want to make a prediction. Okay, so we discovered this in 2019. It was a really big deal to us at the time, and we would go out to conferences and present this, right? And AGU is either the week before or the week after NeurIPS, the main earth science conference, the main computer science conference are like back-to-back weeks. And I remember one time we were giving these talks and we showed this plot in both conferences, and we said, okay, the traditional hydrology models here, regional means it's the model's calibrated on all the watersheds in the 532 watersheds in the United States. Local basin means the model is separately calibrated for each watershed, and it should do better when it's separately calibrated for each watershed. These are some traditional hydrology models. And this is the machine learning model, which has the opposite effect. And so when we showed this showed this plot back in 2019 at AGU, the response we got was, okay, these guys are, idiots who know nothing about hydrology, and they clearly got this wrong, because everybody knows that if you calibrate models to an individual location, that's when they're going to be the best. And then we took the same plots to NeurIPS in front of a machine learning audience and said, look at this amazing result. This is going to open the door to global scale flood forecasting. The response was, these guys are idiots. Everybody knows that if you train a model on more data, it does better, right? Okay, so anyway, the results are true. They've been true for 6 years. They haven't failed, so we're sure that they're true. And we also had this result. This is the result that really gave us the runway to do the project, which is that we took there's two sort of flood forecast, national flood forecasting systems in the United States. For those of probably most of you know, they're both run by the National Weather Service, which is under NOAA. There's the river forecast centers. There are 13 river forecast centers in the United States. Those are the ones that run the operational flood forecasting models that you likely will get an alert from if you get a flood alert on your cell phone or in the newspaper. These are produced by one of 13 regional river forecast centers. And these are where the operational hydrologists come in, they look at their area every morning, they run in 2 shifts usually, depending on the center. They sit down every morning at their computer screens. There's an in-house meteorologist that gives them the weather data that's tuned specifically for the flood forecasting problem. And they run this model called the Sacramento Soil Moisture Accounting Model. I think all 13, I don't know this for sure, but I think all 13 centers run the SAXMA model, which is the Sacramento Soil Moisture Accounting Model. And they do data assimilation, and they tune it by hand, and they do all this work to it. And then the National Weather Service also runs the U.S. National Water Model, which is run out of Tuscaloosa, Alabama at the National Water Center. And this is intended to be sort of a backup. Maybe you could argue it's an experiment in nationalizing the flood forecasting, operational flood forecasting. It is run operationally. It's a model that was built and mostly built at NCAR on contract. And so we have the Sacramento model here that has been tuned. So these are the 530 basins we're going to do experiments on in the United States. We're going to run the Sacramento model. We're going to calibrate it separately for each basin. This model was calibrated by NCAR, not by us. And NCAR did a really, really careful job of calibrating this, almost certainly better than the RFCs can do because they put a lot of time and effort into it. And so this red line represents the model calibrated individually at each basin, and that's the model that you're getting your US flood forecast from. NSE is basically the hydrologist version of an R-squared score, so higher scores are better. And these curves are the distribution of, I should have explained this in the last plot, these curves are the distribution of those 530 gauges that exceed a particular score. So it's 60%, the red line's about, let's say, 0.4, so you have about 40% of the basins, 532 basins are scoring at least an R-squared of 0.6 over the 532 catchments, right? So you want to be further this direction. Better is further this direction. Apologies for not explaining that in the last slide. Okay, so the national water model, the per gauge Sacramento model, and our model, which is the yellow line, but regional, meaning that we took 10% of the basins out, trained on the other 90% and predicted the 10% that it's never seen. And we did that 10 times to get predictions at every location. And so the red model is gauged, the yellow model is ungauged. So our predictions out of sample are doing better than the US national predictions in sample. Great. Okay. Sorry. I'm really sorry. I knew that was wrong. The star is us out of sample. The starred line is us out of sample. Really sorry. I hate when I overstate my results. The starred line is us out of sample. The yellow line is us directly comparing, the solid yellow line is us directly comparing to the US models. Okay. So on average, we're able to do better than the US models out of sample. Okay. The difference is not as large as I originally made it. Apologies. Been years. I've been giving this lecture on this slide for years. It's quite embarrassing. Okay, so we took that and at Google, what we did is we expanded that globally. We built this global model. We published this paper where we compared with ECMWF, which at the time, back in 2024, was the only other global flood forecasting model. And basically, the takeaway is that precision and recall scores, we're getting about 40% precision and recall, meaning that we correctly predict about 40% of the floods that occur. And 40% of the time when we predict a flood, it's correct, which seems very low, but it is a lot higher than 0. And it is also a lot higher than ECMWF's model. The ECMWF's model is about 30%, and our model hits about 30% at 5 days lead time. So we get about 5 days extra warning compared to the ECMWF model at the same skill. And is that useful skill? That really, really depends on your application. But for the IFRC, who's the ones that are absorbing our alerts and turning them into action, that is very useful skill and easily achieves the bar for this being worth them using for early action protocols, right? Okay. So so that's the current state. That's the current state of the art for global flood forecasting. That's the best skill that anyone's ever gotten. Okay. We worked with several countries to understand how good this skill is relative to, forgive me, I'm just going to skip this. I think we have better things to talk about. Okay. So what's the next step? Well, right now we're predicting riverine floods, and we're applying some machine learning models on top of our river predictions that mix exposure with the hazards so that we can understand who we should warn, when, and why. But there's a lot of other data out in the world about floods, right? Remember those SOS alert guys, people that are aggregating text data from social media, from the IFRC, from disaster response agencies, and from news articles? So we can actually mine all that data, of course, now with Gemini. So what my colleagues did here is they built a data processing routine that starts with going to the back end of Google search and saying, how many web pages in the whole world mention floods? So we gathered every web page in the world that mentions floods. And then we filtered those. We used Gemini to filter those based on which of those web pages are talking about a flood that actually exists rather than just flood risk or a law about flooding or new flood maps or something like that. And we hand checked a large sample of those. And then of the ones that talk about a specific flood event, we deploy Gemini to extract the date and location of those flood events. And we achieve about 90% accuracy in doing this. So we've read every web page in the world. And of the web pages that talk about a flood that actually occurred, we're able to extract the date and time of that flood with about 90% accuracy. And then we trained a model. Okay, so this model now does something different than our previous model. This model now includes floods all types of floods. It doesn't know or care what type of flood it's predicting. It's just predicting whether a human being is going to write a news article that a flood occurred at some point in time, right? And it takes weather data as inputs. It takes geophysical data as inputs. It takes human geography inputs. It takes physical geography inputs. It takes climate inputs. It takes all of the normal things. It takes soil type, vegetation type, elevation, topography. It takes all of the normal things that you would take to predict a flood, but instead of predicting a flood, it predicts whether someone's going to write a news article about a flood. Okay. And it does a pretty good job. So these are our latest results. This model went live in February, so it's only been about a month we've been allowed to talk about this. But take a look at the United States plots. So the US, at least academics, archive every flood warning that the US produces. So we have an archive of every flood warning that the US has produced over the last, I don't know, several decades. And we can ask the question, what's the precision and recall of the US flood warnings in actually predicting a flood? And we can ask the same question of our model that predicts news articles. And we can see that we get, these are precision recall curves. So we have a choice about what probability level to take as a positive or negative, which determines how we trade off precision and recall, which is false positives versus false negatives, basically. And of course, we don't have that choice with the archived US predictions because they've already made that choice and we can't adjust that for them retrospectively. But at the same precision and recall scores, we're doing about as well as the US models in the United States. And that's notable because the US National Weather Service is using national and sometimes even local weather data, and we're using global weather data. So we're using the same weather data products in the United, which is ECMWF and GraphCast. So that's the European weather forecast and Google's weather forecast. We're using the same weather forecasts in the United States as we are in Namibia, right? And so we can't prove that we can get the same skill globally because we don't have anything to benchmark it against, but we can say that the model, it's one global model running over the whole world, and there's no particular reason why we should be better in the United States than other places, except that maybe news reporters are better at writing news articles in the United States than other places, which is a possibility. But we're able to get, in the United States, we're able to get the same skill essentially as the National Weather Service, but we're able to do it with a much lower quality data set, input data set, okay? What we're doing now, and I know this lecture is being recorded, I hope I don't get in trouble saying this, is we're kind of marrying these two models. We're asking the question, what does it look like to build a model that predicts both, multi-dimensional, multi-different types of hydrological data, soil moisture, snow cover, vegetation data, river stream flow data, and also predicts this human readable data. And I'm not going to say more than that, just the fact that we're building it. Okay. So this is what the output of this, we call it a flash flood model. And the reason we call it a flash flood model, it's not a flash flood model. We call it an urban flash flood model because we want to stress to our users, which again are mostly NGOs and IGOs, that this model is actually able to predict more than just these long temporal onset riverine floods. It's actually able to predict any type of flood. They mostly care about flash floods, but it's actually not making a distinction between floods that occur in the next 6 hours versus floods that occur in the next, several days. And then what we do is we run this at a fairly coarse resolution and we give warnings. So this is fairly similar to what the National Weather Service does, but we use regular polygons over the whole world instead of these bespoke polygons that represent geological features that have been set up by hand over time at the RFCs, basically. Okay, so this is what it looks like on the map. Yeah, and you can go see it yourself if you want. Okay. And I want to say, I think, two more things, if I remember my slides correctly. One is about science, and one is about the community. So I want to just give a few unsolicited thoughts on what I think is happening with AI and geoscience as a whole. And this graph here kind of shows the progression of my career personally. So this is quite a biased take for sure. But, you know, we've been doing a lot of physics. And I know Dara was around when the hydrology community made a strong and hard-fought push to be more physically based. I think the marker for that effort in my mind, looking back on it, not being there at the time, was the Blue Book by Pete Eagleson in 1991 that really said, okay, hydrology needs to be another branch of geoscience. We need to understand what's going on in order to rely on the predictions that we're making. And that's the world that I grew up in. And that's where we're building models based on concepts, include physics. And then we started to see signals. Many people, including myself, started to see signals that we were getting a lot of information from data that our physically based models were not able to capture. We were able to train some machine learning models on some really basic hydrology data and get better results. And at the time, the way that we interpreted those results, this was back in the early, for me, it was in the early 2010s, but there were already people that had been working on this their whole career. We were saying, okay, well, there's definitely room to improve our models, and because we can see that there's more information in the data than we're able to extract with our current models. So we started asking, how can we, machine learning is really good at extracting information from data. Actually, that's all it is. Machine learning is not models. Machine learning is just tools for extracting information from data. And so what we started to do is, how can we use machine learning to extract more information from our data? We were doing things like diagnosing the errors in our models. We were doing things like adding pre-parameterizations, adding uncertainty distributions on the outputs. We were playing all these games, adding machine learning enabled data assimilation, and we were adding post-processing, bias correction, and we did a lot of this work at the beginning. And we found that I have one paper that I really like here where we took the US National Water Model and we put it as inputs to a machine learning model, and we compared it against the US National Water Model without the machine learning bias correction, and we compared it against the machine learning model. And adding the US National Water Model to our machine learning model only cost us about 2% accuracy. So, okay. So that was quite an achievement. It took a lot of work to get there too, because it was really causing harm. So then we moved to this sort of physics-informed machine learning, which is what is probably in my sort of subjective estimation, probably the most active area of research in hydrology right now, which is how do we add physics to machine learning? And we did a lot of that work. I could tell you about years and years of that work that we did, but I'll just tell you the following story. Every time I added physics to my machine learning models, and I'm talking about really simple models, all I'm trying to do is predict stream flow. I'm not trying to like solve the world's water balance or predict the changes in water under climate change. These things are completely different problems. I'm trying to predict stream flow over the next 7 days. And every time I went in and added a piece of physics to my model, whatever that might be, soil moisture, snow, whatever it was, my model got slightly worse. And there's a mathematical reason for this. It's called the data processing inequality. There's a theorem that says that any function can only subtract information from data. The best possible model can only preserve the entire information content of the data. That's just a mathematical fact if you measure information from the Shannon information theory perspective. And we were seeing that adding these equations, we couldn't find one that was adding. So I went out to Amazon and I bought a copy of my first hydrology textbook of the first hydrology class I'd used, which of course by then I'd completely, probably in grand celebration, gotten rid of this textbook at some point in my career. It was Chow, I think 1980, if I remember right. Anyway, I looked in this book, I said, okay, what's the most basic hydrology equation? It's equation 1.1.1, and it's the mass balance equation. So I sat down for a week and I wrote out the equations that would let you build a neural network that conserves mass. So you can actually embed a conservation symmetry into a neural network, and it turns out to be pretty simple. And I did that, and it only lost about 10% accuracy over my And of course, the reason is really simple. The reason is because the rainfall data you're putting into the model, if you treat that as a mass quantity be conserved, it has error in it. And one of the benefits that you're getting from these machine learning models is they're able to learn the systematic error in your input data. So you're losing that ability if you force it to constrain mass. So it's not really a mystery or but it was a little bit frustrating. So we didn't even really publish that paper. We submitted it to a conference, one of these NeurIP type conferences, and it got sent to one of the satellite. It didn't even get in the main, where I was so proud of that work. It didn't even get in the main conference, okay? And okay, so we abandoned that after years of fighting that battle, and we started building AI models on concepts. So we would preserve the physical variables as concepts in our models. And we currently have a big NASA project to do this, where we're building models that kind of like have a bubble. If you think about a concept graph, they have a bubble for each physical variable we care about, and then we build the machine learning models that are asking the question, how do we learn from all of these multimodal, multi-timescale type data, and in a way that lets the model learn the interactions? And that can work if you're really, really, really careful about it, but mostly what it's doing is it's just learning, it's just taking a giant neural network and separating chunks out to predict each variable. That's mostly what it wants to do if you just let it go, right? And so what the really serious machine learning groups are doing now are these geofoundation modeling things. And that solves this problem. You just throw, basically, they're hard to build. I don't want to trivialize the project, but basically you just throw all of the data you have at it. You don't ask it to treat one piece of data as input and one piece of data as a target. They're no longer regression models. They're these semi-supervised models where you just randomly mask out some data and you have it predict the data that's masked out, and you do it over and over again. And these things learn relationships between data. And what you notice here is that, and that solves the problem. That's basically, in some sense, solves the problem of how do you get models to learn sort of the comprehensive behavior between all these water variables. And what you'll notice is what we had to do to get there is we had to give up everything. Right? So, okay, I don't want to say that this is the answer for everybody. If you're doing climate change, it's really critical that you don't add energy to the system over the next 100 years. If you're doing water resources management, it's really critical that your model doesn't materialize water out of nowhere. I'm not saying that this is a general lesson, but I'm saying that this is the hard-fought lesson that we learned in at least short-term hydrological forecasting over many years. Okay. And the last thing I want to say is social. This is my last slide. You know, we're trying to do it. I'm trying to do a job here. I'm a scientist at heart, and I really like putting slides up like the last one because I can say it in ways that are much less polite than I said it here tonight, if you can believe it or not. And I really like to, watch the reaction from rooms full of academics when I do that. But we're actually trying to solve a problem here. What we're trying to do is we're trying to bring the scale of Google to the problem of giving people information about disasters. And that problem is a sociological problem. That problem is a social problem, right? You can build the best models in the world, and it doesn't matter if no one cares, or if worse, if you come in and you disrupt an ecosystem. So the lever that I have at my disposal to solve that problem, there aren't many, but the one lever that I have found to help solve that problem is trying to be as transparent as possible. And in the world of software, that means making everything open source. So because we don't require a revenue stream, thankfully, thank you, Yossi, for Yossi's the head of Google Research, for making sure, protecting us from that for years and years and years. Genuinely wonderful human being. We're able to publish everything we do, and we're able to make everything open source. So you can go to these QR codes and you can get our real-time predictions. You actually have to sign up for this, and just because I don't know the full story, but in some countries, legally, we have to know who's using these and who isn't. So you have to sign up for this, but it's free. It takes a couple weeks to get permission. This one is our retrospective forecast up through 2024. You can get those for free, and you can use those to tell us how bad our model is. Believe me, many people have done that. And then you can go and get our model code, which is here, and you can actually run our streamflow forecast model with this model code here. It's a training pipeline that almost exactly replicates the model that we run under FloodHub, only the streamflow component at the moment. And then this is the open source data set for streamflow data that we maintain, so you can actually train the model. And if you do it right, no one's done it yet, so I don't know if this actually works or not. But if you do it right, you get pretty much exactly the same, almost the same results that we get for FloodHub. So please try it and let me know. Thanks.
Just going to check the field question.
Questions for Gray?
Easy.
What type of flood inundation model you use?
Yeah, say it again. So.
What type of flood inundation model you use for?
Yeah, okay. So our inundation model is a very simple regression model that trains on satellite data. And this is another one of those really hard fought battles. So the inundation model was actually the first model that our team, this was before I came to the team, that our teams tried to build. And what they first tried to do is they first built a fluid dynamics model sometime, and then they tried to say, okay, we're Google, we need to do this with AI. So they built an AI solver for the fluid dynamics, but it was still fundamentally a fluid dynamics model. And then they started doing some training on satellite data, and they found that the models trained on satellite data were doing a lot better. And they had the reason for that, by the way, was that the DEMs are the largest, the digital elevation maps are the largest source of error. So they found out that they could remove. So here's an example that this team always gave. This was my team before I got there. Always gave is there's a farmer might cut a irrigation trench, and that'll cause an entirely different village to flood. And there's no way that you can see this in the digital elevation map. And this was causing really, really large errors, especially in the places that we care about the most, which are some of the hardest to predict. So we found that training on satellite data and just removing all of the physics from the model was the best results we could get. And so that's what we do. Yeah. Yeah. Yeah.
Big problem around here now is we have tropical storms, high intensity, short duration, localized.
Yeah.
So when you say you can predict flash floods, that I'm thinking, well, is that what we have to deal with? And how do you predict flash floods are controlled by microclimate, are controlled by I don't know how those events are created in the atmosphere. How can you get that small grain from an atmospheric model? Or
It's absolutely true. And that's why you see, look, I keep telling you how good we are compared to others, but let's look at how good we are like in absolute sense. And you're going to see that we miss, more than half of the events. And that's just the reality of it. And the reason, by the way, is the quality of the precipitation data. So when I talk about the world that I want to live in, when we talk about the alerting side, I want governments to give us forecasts everywhere. My dream and my explicit goal that I work for every day is to put myself out of a job. I should not be here, and because we want national governments to do this. But part of that is that national governments should be running their own weather forecast models, because this is where we get, and they should be installing radars. They should be, one of the things that I think is the most important, that maybe I didn't say it explicitly, is the capacity development grants that are being, given to countries through the World Bank and the the IMF. And these capacity development grants go toward a range of things in the weather forecasting space. Some of them are radars, some of them are data collection efforts, some of them are computer systems, early warning systems. But the data collection efforts that let people install, especially radars, in situ, and then it's very common practice now for a major Met agency like the Norwegian Met Agency or the Chinese Met Agency to come in and take one of their global models and help a country build a more local, high resolution model. And we really want to see that everywhere. And I would just say, we're not as active. Look, I don't work in the weather side of Google. I work in the flood side of Google. But their code is also open source. And they really want people to figure out how to use this more cheaply and more efficiently, because what we want is a world where governments are running these things themselves and can do the high resolution and can incorporate the local data. That's all I have to say about that. Great. Fantastic. I don't want to get alerts from universities, but if you can get the data, that's amazing. Yeah. Yeah.
quick question for you in regards, in regards to your work on extreme flooding in ungauged areas. How do you kind of generalize your ML model for hydrologically diverse areas? How would you do something like that?
Yeah, so the answer to that, also an answer one through a lot of effort, is we just put all the data into one model. So we can think about the range of things that we don't do, which is balance our data sets, right? So maybe we have fewer observations of extreme events. We don't oversample those. We don't try to cluster the hydrological regimes and then use those clusters or train different models on different areas. We've tried all that. The best possible generalization that we get is putting all of the data in one model and training the whole thing. And if someone, this is the thing that sometimes I have private silly bets with my colleagues over lunch, and this is probably the one that is probably the strongest bet that I have, which is that I think somebody will figure out how to do better than that. And as soon as they do, I really look forward to reading that paper. Yeah. We actually only go to Android devices. Yeah. Yes.
A lot of the interaction of the model, physical model, comes from satellite data. And where do you see that as the next step to get more data to the model? Like,
Yeah.
what are you looking for to identifying that? And what do you think are kind of the next steps there of working on the
Yeah.
itself, right? You need more data out of it to get the model.
Yeah. Great question. If someone could invent a SAR without speckle, it would change my life. So we're hopeful for a NISAR and SWAT to give us river data in places where we don't have it. We actually aren't working on that. So, you know, if I had a student, which I don't have students anymore, but if I had a student, the project that I would encourage them to work on is taking a global model that's trained on gauge data and asking the question, how much extra value do you get by putting river data specifically from SWAT and NISAR? Yeah.
Arup, I don't know if we can actually let you talk. So maybe you can type your question in the chat and then Greg can answer it.
Any questions? Two questions and then a rope and then the.
Yeah, I guess quick question, just someone with more of a specifically civil engineering background. I'm still trying to wrap my head around the whole, you know, a function can only lose information, you know, sacrificing physics or just extracting raw data. Don't want you to have to give a whole primer on information theory, but if just key resources you have would be much appreciated.
Cover and Thomas, 1991, page 34. Cover and Thomas, yeah. No, the intuition here is okay, pretty simple. I don't think it is. I do want to say one thing about your question though. The data processing inequality is a mathematical fact, and that is not related to the fact that adding physics has not helped, right? What I'm saying is that when we got the empirical result that adding physics doesn't help, I can explain it by pointing to this mathematical fact. It is, so you can, in a cartoon world, neural networks are universal approximators. In a cartoon world, which is nothing similar to reality, the neural networks will extract all the information from data. So you have a high bar, and that's not true in reality. That's just a cartoon, but it does mean that you have a high bar to beat. So it means that if you're adding structure to those neural networks that makes it harder for the training process to learn around, then you could be adding regularization that helps, but you could also just making the training process stiffer. Yeah.
Dan and then group. Well,
with based on the idea that your more generalized or generalist models seem to often do better than the more specialist boutique models. Do you have a sense of how that applies to the scope of your questions as well? Like, is a flood forecast model specifically, should you be throwing everything else, every other data set you have on Earth at it? Or like, how do you draw those boundaries scientifically at all, or just in terms of what data you can actually manage to stick into it?
Yeah, so mostly we've just found more data is better. That's not always true. I did give an example where we added the national water model and it really did cause a decrease in scale. Like it really did. But mostly, I mean, Mostly our approach has just been adding whatever data we can find. And there are a couple times we've taken data out. There's some features, static social geography type features that we added and that caused problems because there were just weird outliers, weird numerics, categorical data that didn't behave. That kind of thing. But yeah, yeah, in general, I think just more data is better. Yeah, absolutely. Sorry, I'm just going to take a minute to say something. One of my favorite comments about this. I have this theory. This is an untested theory. You're really getting me unfiltered here. But as a hydrologist, it's common knowledge. I don't actually know this is true. It's common knowledge that precipitation is the largest source of uncertainty for hydrological forecasts. Okay, and precipitation is arguably the weakest, or at least one of the weakest, highest error data products coming out of a numerical weather prediction model. I've said that in front of lots of atmospheric science audiences and never had someone contradict me, so I'm doing it again here tonight. But anyway, it's certainly some degree of truth to it. And what we're doing is we're taking precipitation data and feeding it into a hydrology model, which was necessary when your models are based on conservation laws, physics equations. You need water input to give water output. But in machine learning, you don't need that. So I can't figure out why my team and me specifically is not going home tonight and building a regression model from the dynamical core, like the pressure fields of a weather model, the actual variables that come out of a Navier-Stokes equation that are much higher quality, much lower uncertainty than the precipitation data that comes out of the physics wrapper of a weather model, right? And just training that directly to predict stream flow. My strong hypothesis is that if we did that, if someone put the effort into doing that, that you would get better precipitation predictions because there's a lot of information about stream flow, about precipitation in stream flow and soil moisture data. And you would also get better stream flow predictions because you don't need to introduce this error to precipitation and then try to unintroduce it through the hydrology model. It's just a hypothesis. Let me know if you build that. I'll love to see it.
So the last note, the question from Aru. The first part is, I believe, a light note. It's nice to end the evening. I hope it's joking, but the last question, the last 3 lines, is a serious, very well thought, serious question. He's talking about, do you see the same, meaning adding physics degrades performance, if the focus is on extremes, meaning unseen extremes?
Yeah, so we had a paper. One of my grad students, Jonathan Frame, had a paper where we did that experiment. Of course, when we talk about adding physics to machine learning models, there's an infinity of ways to do this. And my favorite is the one that's most complex, not necessarily the one that works the best, the one that has the fanciest math, which is where we took this conservation law, turned it into a symmetry, embedded it into the structure of a long short-term memory network, came up with this thing we called a mass conserving LSTM. So is that the best? I don't know, but it's the one we tested on this question specifically. And what Jonathan did is he took years of data with high return period events and left them out of the training set and trained on all the rest of the data so he did this with, I do have this slide. Hold on, I'm going to try to show you the slide. Sorry if I'm taking extra time here. It's right here. I have all kinds of stuff I would have loved to told you about. Yeah, okay. Well, it's the important parts of the graph are hidden, but this is basically training on events, on years of data that have a maximum of 5-year return period events in them, and then predicting on years of data that have, different levels of return period events. And in that US data set, those are the sample sizes for each of those single years of data. And then here we're looking at the absolute percent error of the peak flow of that largest event in the holdout years. So lower is better. And what you're looking at is the difference between the blue, which is the pure machine learning model, and the orange, which is the mass conserving machine learning model. And then you compare that to the Sacramento model, which is green, and then the National Water Model is this sort of dotted line because we weren't able to perform the calibration experiments on that as well. So this model has been trained, this gray model has been trained on data with all of the return period, has been calibrated on data with all the return. So yeah, skill goes down, but the physics in this particular case didn't help. Yeah. I didn't expect so many questions about physics informed machine learning from an engineering audience, but okay. To kind of took a roll of the dice on that one. No, so look, okay, I'm going to end with a personal story to answer this question. I spent my entire young career writing grants to do machine learning and hydrology, and I didn't get a single one of them funded. I played this game, I told Dara this earlier. I played this game where I submitted a grant to a program, in this case, the terrestrial hydrology program at NASA, about machine learning for data simulation, and it was rejected because it wasn't science. This was a direct quote. It wasn't science because it wasn't learning something physical about the system. Then I submitted the exact same grant, the next year, but I took out the words machine learning and called it something else, and it was funded. Okay, so part of my job in this community is to let's put it this way, sacrifice a little bit of my future career opportunities to be an asshole about it. Okay, so someone out there needs to take the perspective that it's not a given that physics helps and that we should test these as hypotheses. And I see this over and over and over and over again. I see the NSF and NASA and the DOE funding literally millions and millions of dollars of grants on physics-informed machine learning without first having tests that show that the physics is going to help in this way, or even without first finding a specific problem with the machine learning model you're building that needs to be fixed and with a legitimate hypothesis. So when I say these kind of things, I'm being a little bit intentionally provocative, but I'm trying to play a particular cartoon character here and trying to ask you to, when you think about these questions, to seriously ask, like, why are you bringing physics to this problem? Why are you bringing machine learning to this problem? Like, what are you, like, is there evidence that there's extra information in the data sets that you have? Because machine learning won't help if you don't have data sets that have information that you're pretty confident you haven't been able to mine all the data out of. So that's what I'm trying to do when I say these kind of provocative things. Thanks.
That note, I would like to thank Gray.